Good morning to all of you. This is Dr. B. Om Prakash Shah, working as assistant professor in the Department of Mechanical Engineering, JNT College of Engineering, Anantapuram. In this class, we are going to discuss about the gas power cycles. These gas power cycles are mainly used, mainly used in internal combustion engines, which are how the power is developed based on the cyclic operations, which includes all the four operations, mainly the suction stroke, compression stroke, and expansion stroke, and the exhaust operations. How the heat energy is developed and how the heat energy which is utilized based on all these operations, we try to discuss with the help of PV diagram and TS diagrams, and how much of the power is developed and what are the important factors which are includes the development of the power for the internal combustion engines. So that in this case, what are the important gas power cycles are there? These gas power cycles are classified based on usage of fuels and based on the ignition systems and all different considerations. We are mainly focused. We are mainly focused on. We are mainly focused on the multi-cylinder spark ignition engines. Here just the spark ignition or SI engines, how the operations are existing. This one is the gas power cycles or the classified classification. Ideal cycles and internal combustion engines, mainly auto cycles and auto cycle. This is in the spark ignition engines or SI engines, and the diesel cycle is the compression ignition cycle, and Brayton cycle and a combined cycle are dual cycles. Just the ideal cycle, just before discussing the ideal cycle, these are we made some of the assumptions. These assumptions are air is working fluid and circulated in the closed envelope is an ideal gas, and exhaust and air intake are substituted with the heat transfer from the system to the surroundings. Combustion is replaced with heat transfer from an external source to the system. All the processes are initially reversible, when the gas specific heats are constant, which you use the specific heat at constant pressure or constant volume. The cycle does not involve any friction, and the pipes connecting the components have no heat loss, neglecting the charges in kinetic energy and potential energy, where the all the assumptions were taken into consideration for the ideal cycles. And coming to the next one, the heat engines are mainly it produce the maximum power with the help of Carnot cycle. This Carnot cycle is existing two isentropic operations and two isothermal operations, and how the heat energy is develops and how the heat energy is releases. Just these heat energy in and heat energy is out at the but at the isothermal operations only, isothermal compression and isothermal expansion operations. These are it is represented in the PV diagram and the TS diagram. Just we observe in this operation, air is suction takes place, and 3 to 4 this is the in the compression process. 3 to 4 is the isothermal compression operation. In this isothermal operation, the heat is out, and then the isentropic compression operations. Just you observe the isentropic operation, isentropic expansion of isentropic compression process. In this isentropic compression process, the pressure is increases from P4 to the P1, and the volume is decreases from V4 to the T1, and then the heat is released and heat is it is added into inside the combustion chamber here. That is in the constant isothermal expansion operation. That is one, and two, in this isothermal expansion process, the heat is added taking place, and then this same heat energy which is try to utilize for the mechanical work, we try to convert the maximum mechanical work. And second one is the exhaust operation. That is the last one is the expansion operation, that is isentropic expansion operation, which is the pressure is decreases from P2 to P3 and volume is increases from V2 to V3. So that the which includes all the four operations and cycle is repeats. We are coming to the next cycle is this is actually the Carnot cycle, and the next cycle it is the Otto cycle. And the Otto is the inventor of the four-stroke cycle, and he is basically from German, and he was born on 14th June 1831 in Germany, and he develops the Otto cycle based on the things. Before discussing all these basic operations, we try to get some clear information about some new terminology here in case of the piston and cylinder arrangements. What is the bottom dead center, top dead center, and clearance volume and compression ratio? The bottom dead center is the piston is reaches the bottommost position in the combustion chamber. That is, we simply consider the bottom dead center, and top dead center. It is the tree whenever while the piston is moving and it reaches the topmost position inside the combustion chamber, that is the top dead center. And the clearance volume is the top dead center of the the cylinder head. That is simply considered as the minimum volume, that is clearance volume. And compression ratio, it is the compression ratio. We are defined in two ways, based on the volume and based on the pressure attained inside the combustion chamber. So always a compression ratio, it is greater than one only, based on volume, the total volume of the cylinder to the clearance volume, total volume of the cylinder to the clearance volume, are simply the volume before the before compression process to the after compression process. Before the expansion process, it is the summation of the clearance volume plus the stroke volume, and the after compression process, the volume is existing only the clearance volume. So the displacement volume, or simply consider as the stroke volume, the volume is existing in between the top dead center and the bottom dead center. And the mean effective pressure is the main average pressure is existing inside the combustion chamber while the all the operations are existing that takes place. It is, we simply denote, it is the ratio of net work done to the work volume displacement, or simply the stroke volume. So that this is the mean effective pressure. It depends upon the net work done to the work the what stroke volume. The stroke volume, or the things are simply the main effective pressure is the net work done to the volume, maximum volume to the minimum volume. And these are the auto cycle operations. Just we observe the pressure the PV diagram and TS diagram here. In the TS diagram, the PV diagram, just you observe this auto cycle. It consists of the four operations, two constant volumes and two isentropic operations. In this the first operation is the isentropic compression process. In this isentropic compression process is 1 to 2 is the isentropic compression process. In this isentropic compression process, the compression takes place and pure air fuel mixture is compressed and the pressure is increases from P1 to P2 and volume is decreases from V1 to V2. At the end of V2, at the end of reaches the point 2, it is with the help of the spark plug, the spark is initiated and it is the combustion process taking place, and some of heat energy is added into the system, and some heat energy is added at constant volume operation, that is the operation 2 to 3 is heat addition at constant volume, and then the expansion process is taking place at the isentropic expansion operation, or simply this is the power of a power stroke only. In this power stroke, piston is moves from top dead center to the bottom dead center, so that pressure is decreases from V3 to P3 to P4, and volume is increases from V3 to V4. So in this case, and then the heat is losses at the end expansion operation in this exhaust operation at constant volume operation, that is V4 to the V1. So we discuss with the help of some suitable expressions here, some suitable expressions. Just we observe how the heat and the air is air fuel is mixture is entered in the suction stroke and power stroke in the suction stroke, and how the operations are existed takes place. Just we observe all these four operations: compression, power, and exhaust and intake operations. How the heat energy is rejected takes place only based on in the exhaust operations. Just we observe all the four diagrams with the help of PV and TS diagram, how the pressures and volumes are attained at the auto cycle. And coming to picture, it is gives the very clear operation. It gives very clear operations about all the auto cycles. And coming to the auto cycle operations, the efficiency is defined the useful work with the heat input. The useful work is simply or network done is the heat availability, heat input to the heat input. Mm, Total heat energy is available to the heat input and the thing by the heat input. These are thing H is the heat input and HL is in the case of this one is heat. At the low level, simply we consider all the things with the help of Q is directly proportional to the M mass, and Q is directly proportional to the temperature gradient. If suppose we heat is added at constant volume operations, the but proportionality constant we replace, where eliminate the proportionality constant, we replace constant specific heat at constant volume operation, that is the C suffix V. Finally, what we are simply would uh, simplify the equation, and finally in terms of the volumes and in terms of the volumes and compression ratio, the efficiency is 1 minus of V2 by V1, and gamma minus that is the isentropic induction isentropic induction, and the isentropic operations, and in ideal gases, just the thing the R suffix V is the compression ratio, and this is the thermal efficiency. This is the scenario of the thermal efficiency and the compression efficiency. That is a simple scenario, and efficiency is 1 minus of 1 by r suffix v to the whole to the power of gamma minus 1. And these are efficiency of Otto cycle and compression ratio, how the path, the orientation of all the things are existing. This is the compression, the index k value, it is goes on increases. What happens, what typical the orientation of compression auto cycle and compression cycles. And they just you observe all the things. And here, and the next one, we are coming to the diesel cycle. In this diesel cycle is the heat added in constant pressure, and heat is rejected in the constant volume operation. In this spark, the thing, just we observe the actual cycle and diesel cycle. In this diesel cycle, heat is added in the compression process, and heat is rejection in the constant volume operation. And just to observe the PV diagram, and we try to observe PV diagram and TS diagram. 1 to 2 is the isentropic compression process. In this isentropic compression process, volume is decreases from V2 to V1 to V2, and pressure is increases P2 P1 to the P2, and heat is added at constant pressure process, that is the 2 to 3, and the heat is added, and the expansion process is attained. The expansion process is 3 to 4, and last one is 4 to 1 is the power process. Same, just the net work done is the heat input to the heat output, and the efficiency is net work done to the heat input. It is very simple operation. Just we follow the same concept as like auto cycle, and finally we try to simplify the equations. The how the how to try how best we try to, this is the cutoff, we are taking the cutoff ratio. Cutoff ratio, it is defined as the volume at the cutoff to the clearance volume. The air standard thermal efficiency of the Otto cycle and diesel cycle is these are the expressions. Just we try to observe, and the only thing is the cutoff ratio is coming to the picture in case of the diesel cycle. And same as the auto cycle, the compression ratio, how the with the help of the compression ratio with the efficiency of the diesel cycle, diesel engine, diesel cycle, how this orientation it is goes on, the based on the compression ratio is with the increases. This is the efficiency of the this is decreases here. And then these are coming to the Breton cycle here. In this Breton cycle, where the two constant pressure, the constant pressure operations, and two isentropic operations are existing takes place. In this Breton cycle, heat is added at constant pressure, and heat is rejected at constant pressure operation only. And this Breton cycle is existing. These are the four operations. 1 to 2 is the Breton cycle, isentropic compression, and 2 to 3 is the constant pressure heat addition. 3 to 4 is the expansion operation, isentropic expansion operation, and 4 to 1 is the constant volume heat rejection. This is the and the expression of efficiency of the Breton cycle based on the temperature limits. Final in terms of the completion ratios, and the proportionality constant. And this is the thing. And finally, the actual gas turbine cycle is the working based on this only. With this, we conclude these uh, topic.